So again, we need to identify just a little bit further what are our ROS? Like, what are they? How do they come up? Where do they come from? How are they disposed of? What do we need to do? So, three molecules in particular make up the majority of reactive oxygen species, and those are a superoxide ion, hydrogen peroxide, and hydroxyl radicals. Okay, so you don't need a chemistry degree to really get this. I'm going to break everything down just a little bit more, but so superoxide is a oxygen molecule, O2, with an extra electron, and that extra electron makes it much more reactive. Oxygen itself is already reactive, right? Think oxygen to a flame. It kind of like encourages the burning. Um, Hydrogen peroxide, we're all familiar with that. H2O2. It's the bubbly liquid that you put on wounds to help break things down and heal. Again, that's a literal connection to the healing process. If you need to disinfect and get rid of bad things in an open wound, pouring ROS on this reactive oxygen species, hydrogen peroxide, is a means of getting your immune system active to clean the wound. Okay, so hydrogen peroxide is incredibly reactive, and then hydroxyl radicals are kind of a result of the breakdown of hydrogen peroxide, which can be reduced by an exchange of molecules and electrons to turn into a hydroxy molecule, which is just regular OH minus, but this has an extra electron. That extra electron makes it much more reactive with other substances. Again, a little bit extra, but again, it's important to know these three: superoxide, hydrogen peroxide, and hydroxyl radicals. So, okay, Bowie, we've gotten into why ROS are important, right? They are important because they signal for repair. If we did not have ROS in our bodies, we would all be dead, right? Because our immune system wouldn't know what needs to be cleaned up and repaired. But when we think of things in the long term, what are the implications and the potentials of these ROS when they've kind of been left to their own devices, right? What's like the mildewy, moldy house after the house fire, right? And it is pretty extensive for humans, right? So signal for repair, that's a good thing. Some of the not so good things: damage of our DNA or RNA, right? So this is at the very base level of the composition of our cells, right? ROS are capable of acting upon DNA structure and altering it, right? This can lead to altering the expression of genes, the order of genes. It, again, important when you think of a disease state, right? Especially for those type 1 diabetics concerned with genetic expression. And then again, if it's acting on DNA, it's going to act on a lot of other things as well. So ROS can also oxidize polyunsaturated fatty acids and lipids. Like this is like what liver spots are and what white hair comes from, right? So lipid peroxidation or lipofuscin, these are all results of excess ROS, liver spots, white hair. And then the oxidation of amino acids and proteins, right? So mentioned before about glycating protein receptors, altering protein function. These are all important for diabetics as well. Insulin sensitivity, insulin resistance, two sides of the same coin, are reliant on protein receptors on the cell in order to enact what it is that they do. if that receptor becomes glycated, which is a result of chronic inflammation in the presence of ROS, that, the shape, the size, the fit of the receptor for insulin changes so that it doesn't bind insulin. That's what insulin resistance is. So not good. Not good to have amino acids oxidized in the presence of excess ROS. And then oxidative deactivation of specific enzymes by oxidation of cofactors. Again, this is kind of an extension of that amino acid and protein function. Essentially, these guys are like Tasmanian devils, just leaving our cells not looking like what they looked like a minute ago before the inflammation got there. So, big point here, and a great thing to remember when you're thinking of oxidative stress. That's a term that gets thrown around a lot too, like an antioxidative stress, right? So oxygen is very reactive, very reactive. Oxidative stress is what is inducing that inflammatory response. So ROS are what result from things being oxidized in the body, as well as causing more oxidation in the body. So how does this apply to diabetes? So how does it not apply to diabetes? So what in a diabetic is inflamed? It's a multi-organ condition, right? The pancreas usually takes the cake because that's kind of like the face of diabetes in terms of its production of insulin and the fact that diabetes is the lack of sensitivity to insulin. But it's not just the beta cells of the pancreas, right? The gut is affected, how we're digesting food, the liver, how that's processing toxins, that can be inflamed, joints, heart, liver, kidney, nephropathy, neuropathy, all of these complications associated with diabetes are because of inflammation, right? So, whatever, you could say nephropathy or neuropathy, the inflammation of kidney tissue or nerve cells is a result of, let's say, high blood sugar, right? So it's like, oh, if you don't manage your diabetes well, you're making it harder for your kidneys and nerve cells to do their job. But a level deeper than that is because having high blood sugar causes more inflammation that first adversely affects your kidneys and your nerves. So ROS is everywhere. Everywhere that you're experiencing issues with, these reactive oxygen species need to be addressed. And then even further, I just made a little side note before on type 1 diabetics interested in the genetic nature of diabetes. So we're concerned on certain immune cells, right? HLA genes, which I talked about in episode 8 of the genetic nature of type 1 diabetes of the same podcast. HLA stands for human leukocyte, right? That's white blood cells. So that's talking about immunity and the fact that those genes very loosely correlate with the diabetic state. But when you look back and think that prolonged ROS exposure can actually alter DNA expression, what's to say that having the genes that are common in diabetics is enough for having diabetes? We've already stated that that's not the case. 95% of the people that have the same genes as those that do have diabetes do not. So all of the quote unquote diabetic genes that we think gave us diabetes, for every 5 of us, there's another 95 that have the same ones and don't have diabetes. So might it have been the prolonged exposure to this ROS, this extended unsolved inflammatory response, that caused the changes that express this diabetic state? I would argue that it did. So I hope this has helped.